solar system, there's a rule that seems incredibly obvious. The closer you are to a heat source, the hotter it feels. If you stand near a blazing fire, your skin will feel the intense heat more strongly than if you were standing in the corner of the room. Based on this simple logic, Mercury, the tiny planet nestled closest to the Sun, should be the hottest place in our family of planets. And yet, the universe is always full of surprises that go far beyond human imagination. Mercury is, on average, about 58 million kilometers from the Sunday. At this breathtakingly close distance, it endures terrible streams of radiation from its parent star. However, the title of hell of the solar system does not belong to it. That position belongs to Venus, the second planet, located 108 million kilometers from the Sunday. To put that in perspective, Venus is nearly twice as far from the Sun as Mercury is, and yet, the average surface temperature on Venus consistently stays around 464 degrees Celsius, hot enough to melt lead. Meanwhile, Mercury, despite being closer, only reaches a maximum temperature of about 430 degrees Celsius, and when night falls, it becomes bone-chillingly cold. This strange difference is not a mistake of nature, but the result of fascinating physical and chemical characteristics. In the next 15 chapters, we will peel back these layers of mystery together. We will learn about the dense atmosphere of Venus, about the extreme greenhouse effect that has turned this planet into a giant heat trap, and why Mercury, despite being so close, cannot hold on to its own warmth. Imagine you are floating in space, with the planets glistening below you like precious gems. The story of temperature, of clouds of carbon dioxide, and flowing hot lava will guide you into a deep and peaceful sleep. In the infinite expanse of the solar system, there is a temperature puzzle that has puzzled many who are new to astronomy. It is the strange contrast between Mercury and Venus. To understand this clearly, we need to imagine their positions in space. The Sun, the giant ball of fire at the center, radiates a terrifying amount of thermal energy. Naturally, whatever is closest to the heat source should be the hottest. Mercury is the one sitting in that very front row seat. Khoảng cách trung bình từ sao thủy đến mặt trời chỉ khoảng 58 triệu km. Nếu bạn đứng trên bề mặt của nó, mặt trời sẽ hiện ra từ gấp 3 lần so với khi chúng ta nhìn từ trái đất. Ánh nắng dội xuống bề mặt đá của sao thủy, mạnh hơn gấp 7 lần so với những gì chúng ta nhận được ở quê nhà. Với sự gần gũi đến nghẹt thở như vậy, bề mặt của nó bị nung nóng lên tới 430 độ C vào ban ngày. Đây là mức nhiệt đủ để nung cháy trì trong chớp mắt. Thế nhưng, điều kỳ lạ bắt đầu từ đây. Sao thủy không thể giữ được hơi ấm đó. Ngay khi màn đêm buông xuống trên sao thủy, nhiệt độ sẽ tụt dốc không phanh. Từ cái nóng như hỏa ngục, nó rơi thẳng xuống âm 180 độ C. Tại sao lại có sự chênh lệch khủng khiếp đến 610 độ C giữa ngày và đêm như vậy? Câu trả lời nằm ở chỗ sao thủy gần như không có bầu khí quyển. Nó giống như một người đứng sát bếp lửa nhưng lại hoàn toàn trần trụi. Khi bếp tắt hoặc khi người đó quay lưng đi, cái lạnh của không gian sẽ ngay lập tức xâm chiếm. Không có một chiếc áo khoác không khí nào để giữ lại những hạt nhiệt năng quý giá. Sao thủy trở thành một hành tinh của những thái cực, vừa là lò lửa, vừa là hầm băng. Now, let's look a little farther out, to the next neighbor, Venus. This planet is about 108 million kilometers from the Sun, which is 50 million kilometers farther than Mercury. At this distance, the intensity of sunlight has decreased significantly. According to basic physics calculations, without an atmosphere, Venus's temperature should only be around minus 45 degrees Celsius. But reality slaps that simple theory right in the face. The temperature across the entire surface of Venus, whether it's day or night, at the equator or at the poles, remains at an average of about 464 degrees Celsius. This is the crux of the paradox. Venus is about 34 degrees Celsius hotter than Mercury, despite being much farther from the heat source. What's more frightening is its temperature stability. While Mercury freezes at night, Venus stubbornly maintains its sweltering heat. It's like a giant oven that has been turned on and never switches off. This difference comes not from how much heat they receive, but from how they hold that heat. Venus possesses an extremely dense and heavy atmosphere, mainly composed of carbon dioxide. It is this layer of gas that has created an extreme greenhouse effect, turning this splendid planet into a heat trap with no escape. Heat gets in easily, but cannot escape back into space. When scientists first launched spacecraft, like the Soviet Union's Venera series or NASA's probes here, they were utterly astonished. The most sophisticated electronics, designed to withstand harsh environments, lasted only a few hours before being crushed and melted by the heat and pressure of Venus. The data sent back confirmed a harsh reality. Being closest to the sun does not mean being the hottest. Mercury may be the messenger of the gods with the fastest orbital speed, but Venus is truly the kingdom of fire. The loneliness of Mercury in the cold darkness and the suffocation of Venus under its thick clouds are two sides of the same coin, showing us the importance of an atmosphere for life and temperature. We have just gone through the first sketches of the temperature difference between these two planets. In the next part, we will delve deeper into Mercury, the tiny planet with a surface full of impact craters, and the reasons why it cannot protect itself from the harshness of the universe. Let us continue our journey together, leaving behind the general concepts of the solar system to get up close to the smallest yet most resilient planet in our family of celestial bodies. Mercury, known to the ancients by the swift name of the messenger planet, is our first stop. In the silence of space, Mercury appears as a grayish stone, full of the scars of time, tirelessly revolving around the enormous heat source that is the Sunday. Mercury is a planet of extreme contrasts. It is so small that it's only slightly larger than Earth's moon. If you could place Mercury next to our planet, it would only be a third of the width. However, don't let its small appearance fool you. Beneath that thin rocky crust is a giant iron heart, accounting for more than 70% of the planet's entire mass. Scientists at NASA, through the mission of the Messenger spacecraft, which stands for Mercury Surface, Space Environment, GE Chemistry, and Ranging, discovered that this iron core has a diameter of about 4,000 kilometers. This means that Mercury is almost a giant metal sphere wrapped in a thin layer of rock. Why does Mercury have such an abnormally large core? This remains one of the greatest mysteries in astronomy. One theory suggests that in the early days of the solar system, about 4.5 billion years ago, Mercury was a much larger planet. However, a catastrophic collision with another celestial body blew away its outer rocky mantle, leaving only the hot iron core behind. Imagine such a cataclysmic event, as rocky debris was scattered into space, leaving a resilient nucleus to continue existing next to the Sunday. Because it is so close to the Sun, only about 58 million kilometers away, Mercury is subjected to immense pressure from the solar wind streams of charged particles ejected from the parent star at speeds of millions of kilometers per hour. It is this wind, combined with the small planet's weak gravity, that has made it impossible for Mercury to hold onto a real atmosphere. Instead of a thick layer of air like Earth's, Mercury only has a fragile layer of gas called an exosphere. This exosphere contains small amounts of elements like hydrogen, helium, oxygen, sodium, and potassium. These elements are constantly being blown away into space by the solar wind and are replenished by cosmic dust or from small meteorite impacts. It is precisely this lack of a sufficiently thick atmosphere to regulate temperature that makes Mercury a place where heat and cold clash in the most extreme way. During the day, when the planet's face is turned towards the furnace of the Sun, the temperature can reach 430 degrees Celsius. To help you imagine, this temperature is twice what's needed to bake a loaf of bread in our ovens. But as soon as the planet rotates and that land is plunged into darkness, All of that thermal energy escapes immediately into deep space. The temperature drops to -180 degrees Celsius in a short period of time. This temperature swing is like standing in a smelting furnace and then immediately being thrown into a vat of super-cold liquid nitrogen. When you look at the surface of Mercury through a telescope or in the images sent back by the Mariner 10 spacecraft in 1974, you'll see it looks very much like our moon. Craters are everywhere, along with cliffs thousands of meters high and gray, rocky plains. These scars tell a story of a violent history, as Mercury was continuously bombarded by meteorites and comets for billions of years. One of its most striking features is the Calorus Basin, a giant impact crater up to 1,550 kilometers in diameter. The impact that created this basin was so massive that it sent shock waves through the planet's core, deforming the surface on the exact opposite side. Another interesting and paradoxical fact is that, despite being the closest planet to the Sun, Mercury may still harbor water ice. Scientists have used radio waves from Earth and data from the Messenger spacecraft to observe the deep craters at the planet's poles. Because Mercury's axis of rotation is nearly vertical, the bottoms of these craters never receive sunlight. They lie in perpetual, frigid darkness, cold enough for water ice to exist there for billions of years without evaporating. This is a testament to how the universe always has mysterious corners, where life, or the conditions necessary for it, can hide in even the most extreme places. Mercury is also a true speed racer. It takes only 88 Earth days to complete one orbit around the Sunday. However, the planet rotates on its own axis very slowly. It takes 59 Earth days to complete just one rotation. This leads to a strange phenomenon. A day on Mercury, from one sunrise to the next, lasts 176 Earth days. This means, if you were standing on Mercury, your day would be twice as long as the planet's entire year. Time seems to be squeezed and stretched under the scorching heat and freezing cold. As we quietly observe Mercury from a distance, we see a lonely planet, with no natural satellites orbiting it and no clouds to shield it. It stands there, bare and resilient, enduring the tremendous power of the sun every second of every minute. This very barrenness is the reason why Mercury, despite being in the prime position to receive heat, must relinquish the title of hottest planet to the one that follows it. Closing the story of this swift messenger, we realize that distance is not the only factor that determines a world's fate. To become a true furnace, something more is needed, something Mercury lacks, but its next-door neighbor possesses in abundance. In the next chapter, we will leave behind the dry, rocky craters of Mercury to journey to a completely different world. It is a place known as the Morning Star, gorgeous and brilliant, yet hiding a suffocating truth. Together, we will explore Venus, the brightest gem in the night sky, and also the hottest place in the solar system. Leaving behind the arid craters and solitude of Mercury, let us glide through space to a more brilliant world. From Earth, if you look up at the sky at dusk or just as dawn breaks, you will see a bright celestial body, shimmering like a diamond suspended in the night. That is Venus, often affectionately called the evening star or morning star. With such splendid beauty, it's no surprise that in Western mythology it was named after the goddess of love and beauty. Yet, behind that lovely facade lies an incredibly harsh reality, a true hell hiding behind its silky clouds. Venus is the second planet from the Sun, located at an average distance of about 108 million kilometers. It is often called Earth's sister planet because the two share many similarities in size and mass. Venus's diameter is about 12,104 kilometers, only about 640 kilometers smaller than our Earth. If you could place the two planets side by side, you'd see they look like a pair of twins. Venus's composition is also similar to Earth's, with an iron core, a rocky mantle, and a solid outer crust. However, that is all these two sisters have in common, because as we delve deeper, we will find that Venus is a completely different and hostile world. The first thing that prevents us from seeing the surface of Venus is its atmosphere. Imagine trying to look through a thick, eternal layer of fog. Venus does not have a clear blue sky like Earth. Instead, it is covered by a thick blanket of clouds, 50 to 70 kilometers above the surface. These clouds are not made of cool water vapor. Their main component is tiny droplets of sulfuric acid. This cloud layer reflects up to 70% of the sun's light back into space, which is why Venus shines so brightly from a distance. But it is this same layer of clouds that conceals a brutal truth below. If you could penetrate that layer of acid clouds to land on the surface, you would find yourself in a dim space with a strange orange-yellow hue. Sunlight struggles to pass through the dense atmosphere, creating a dark and oppressive environment. The surface of Venus is a scene of destruction. Vast plains covered in volcanic rock, towering mountain ranges, and thousands of volcanoes that are either dormant or may still be quietly active. There are rivers of cooled lava that stretch for thousands of kilometers, remnants of violent eruptions in the past. One of the strangest features of Venus is the way it rotates. While most planets in the solar system, including Earth, rotate on their axis from west to east, Venus has chosen its own path. It spins backward, from east to west. This means that if you were standing on Venus, you would see the sun rise in the west and set in the east. Not only does it spin backward, but its rotation speed is unbelievably slow. One rotation on its axis takes 243 Earth days. Meanwhile, it only takes about 225 Earth days to complete one orbit around the Sun day. Thus, a day on Venus is actually longer than its own year. This slow and backward rotation has raised many questions for scientists. Some theories suggest that, like Mercury, Venus may have been struck by a massive object in the distant past, an impact so powerful that it reversed its direction of rotation and slowed the planet down. This slow rotation also contributes to the creation of terrifying winds in the upper atmosphere, where the acid clouds can travel at speeds of up to 360 kilometers per hour, much faster than the most powerful hurricanes on Earth. Exploring the surface of Venus has been an extreme challenge for human technology. In the 1960s and 70s, the Soviet Union carried out the ambitious Venera program. The Venera 7 probe was the first spacecraft to successfully land and send data from the surface of another planet back to Earth in 1970. However, it survived for a mere 23 minutes before being crushed by the heat and pressure. Later, Venera 13 set a record by operating for 127 minutes and sent back the first color photographs of the Venusian surface. Those images revealed a barren and hostile world of orange-yellow rock and gravel. Later, NASA's Magellan spacecraft used radar to pierce through the cloud cover and create a detailed map of the planet's surface, helping us better understand its volatile terrain. When we look at Venus, we see a deceptive beauty. It is as magnificent as a goddess when viewed from afar, but it carries within it a fiery heart and a toxic breath of acid and carbon dioxide. Why would a planet with so much in common with Earth veer onto such a harsh evolutionary path? Why didn't it maintain a temperate climate, instead becoming a gigantic oven, hotter than even Mercury, despite being farther from the Sun? That is the great question we will seek to answer in the chapters to come. We have learned about the barrenness of Mercury and the dangerous beauty of Venus. Now, let your mind settle, feel your steady breath, and prepare for the next part of the story. We will analyze the laws of thermal energy more deeply and discover why distance is sometimes not the only decisive factor in this vast universe. Let your mind continue to drift in the quiet of space, where the sun's rays silently spread throughout the planetary system. After visiting desolate Mercury and admiring the splendid appearance of Venus, we need to pause for a moment to understand a fundamental law of the universe. This is the law that, at first, we all thought would explain everything. But as it turns out, it is just one piece of a much larger puzzle. That is the law of distance and thermal energy. Close your eyes and imagine you are sitting in front of a large bonfire in the middle of a bitterly cold winter night. As you sit very close, the warmth from the fire radiates intensely onto your face, sometimes even feeling scorching. But if you move back a few steps, that heat subsides. If you go to the very edge of the circle of light, you will only feel a gentle warmth caressing your skin. In the universe, the sun is that giant bonfire, and the planets are like the people sitting around it, receiving its warmth. According to the fundamental laws of physics, the energy from the sun doesn't travel in a single straight line, but radiates out in all directions, forming an ever-expanding sphere of light as it moves away from the source. As this sphere gets larger, the energy is spread out over a wider area. Scientists call this the inverse square law. To put it simply, if you are twice as far away, you don't just get half the heat, you actually receive only 1/4 of that heat. This law is incredibly strict and plays no favorites with any planet. Now, let's apply this law to our two friends. Mercury is in the front row seat, about 58 million kilometers from the Sunday. At this unbelievably close distance, the amount of solar energy it receives per square meter of its surface is enormous. Every passing second, Mercury's rocky surface endures a blazing shower of radiation. If we measure it in numbers, this amount of energy is about 7 times stronger than what Earth receives. Therefore, the fact that its surface is heated to 430 degrees Celsius is completely understandable and well within the predictions of physicists. Meanwhile, Venus is farther away, about 108 million kilometers from the Sunday. This distance is nearly double that of Mercury. According to the inverse square law we just discussed, the amount of solar energy reaching Venus is only about 1/4 of the energy reaching Mercury. Although Venus still receives more heat than Earth, compared to Mercury, it's like someone sitting in the second or third row, where the fire is no longer so intense. If the universe operated based on distance alone, then Venus's temperature should be much lower than Mercury's. Scientists have calculated that, with no other factors involved, the surface temperature of Venus should only be around -45 degrees Celsius. You heard that right. It should be an icy world, not an inferno. Yet, reality shows a completely opposite result. Not only is Venus not cold, but it is also more than 30 degrees Celsius hotter than Mercury. And this heat is constant, day and night. This contradiction between the theory of distance and the actual temperature is what makes Venus so special. It shows us that in science, receiving energy is only half the story. The other half, and in this case the most important half, is how a planet retains or releases that energy. Mercury, despite receiving a lot of heat, is a wasteful spender because it has nothing to shield it. All the heat it receives during the day is thrown right back into space as soon as night falls. In contrast, Venus is an extreme hoarder. Although it receives less energy from the sun, it has an incredibly effective heat-trapping mechanism. It's like a house built of glass and wrapped in thick layers of insulation. Once thermal energy gets inside, it is trapped, circulating and accumulating day after day, year after year. It is this relentless accumulation that has pushed Venus's temperature to a record high, surpassing even its neighbor located right next to the Sunday. The law of thermal energy also teaches us about balance. On Earth, we are fortunate to have just the right distance and a suitable atmosphere to sustain life. But when we look at Mercury and Venus, we see two of the universe's extremes. On one side is the harshness of lacking protection, and on the other is the danger of too much protection. The millions of kilometers in space are not just soulless numbers. They are the boundary between life and destruction, between ice and fire. As you lie here, in the safety and warmth of your room, try to imagine the invisible streams of energy crossing millions of kilometers of space. They sweep past Mercury, heating its gray rock before vanishing into the void. Then, they reach the thick clouds of Venus, where they are captured, creating a tremendous thermal pressure. These laws of physics are still operating silently and precisely, creating the astonishing diversity of worlds in our solar system. To conclude this chapter, we have learned that the distance from the Sun is not the sole king that determines a planet's temperature. There is another force, a powerful coat that has upended all the usual rules. That is the atmosphere, something Mercury has lost and Venus possesses in extreme abundance. In the next chapter, we will delve deeper into the concept of the atmosphere. We will find out why a fragile layer of air can change the fate of an entire planet, and why it is the key to unlocking the paradox of heat and cold between Mercury and Venus. In the infinite stillness of space, where darkness and light are in constant battle, each planet emerges as a distinct entity with its own personality. After navigating the dry numbers of distance and the laws of thermal energy, let's pause to explore a concept that is incredibly soft, yet holds the power to change a world's destiny. That is the atmosphere, or as I like to call it, the coat of the planets. Imagine yourself lying under a starry sky on a cool autumn night. A gentle breeze caresses your skin, carrying the scent of grass and the moisture of the earth. All of those sensations, from your breath to the warmth enveloping your body, are thanks to the thin but resilient layer of air embracing the earth. The atmosphere is not just a reservoir of oxygen for us to breathe. It is also nature's most sophisticated climate control system. So, what exactly is an atmosphere? To explain it in the simplest and purest sense, an atmosphere is a layer of gases surrounding a planet or celestial body. This layer of gas is kept from drifting into the vastness of space by gravity, an invisible yet powerful pull, like a mother's embrace holding her children tight. Depending on the planet's size and its temperature, this coat can be as thin as a silk ribbon, or as thick and heavy as a massive down comforter. The atmosphere plays three of the most crucial roles in determining a planet's appearance and temperature. First, it is a protective shield. The universe is not as peaceful as we might think. It is filled with streams of highly toxic radiation from the sun, charged particles that can destroy any biological structure, and millions of rock fragments flying at incredible speeds. When a meteorite hurtles toward a planet with an atmosphere, friction with the air heats it up, causing it to burn and disintegrate before it can hit the ground. We call these beautiful shooting stars. But on barren planets, those rock fragments would slam directly into the surface, leaving deep scars that will never heal. Second, the atmosphere is a distributor of thermal energy. Imagine a giant fan that is constantly running. On planets with air, winds carry warmth from the hot equatorial regions to the frigid polar regions. It helps prevent the temperature difference between the illuminated side and the dark side from becoming too extreme. Without this circulation, one half of the world would be scorched, while the other half would be eternally frozen. And finally, most importantly for our story, the atmosphere is a heat trap. This is where the difference between Mercury and Venus is decided. Sunlight carries energy in the form of short-wave radiation that easily passes through the air to warm the planet's surface. As the surface heats up, it radiates heat back into space in the form of long-wave radiation, infrared rays. If a planet has no atmosphere, or a very thin one, this thermal radiation escapes immediately. But if the atmosphere contains heat-absorbing gases like carbon dioxide or water vapor, they will trap this thermal radiation, reflecting it back to the surface, causing the planet to heat up even more. To better understand the power of this coat, let's compare the three closest siblings. Mercury, being too small and too close to the sun, has lost its coat. It stands naked in space, receiving heat only to lose it all, like a person standing in a blizzard without a coat for protection. Our Earth is fortunate to possess a perfectly fitting coat, a mixture of nitrogen and oxygen with a small amount of carbon dioxide, just enough to keep water in a liquid state and allow life to flourish. And Venus? Venus isn't just wearing a coat, it's wrapped in hundreds of thick down blankets. Its atmosphere is so heavy that the pressure on its surface is equivalent to the pressure at a depth of 900 meters beneath the ocean on Earth. Its composition is mainly carbon dioxide, an extremely effective heat-trapping gas. It is this oversized and suffocating coat that has turned Venus into a gigantic pressure cooker, where the temperature never drops, even long after the sun has set. In the silence of the dark night, try to feel the magic of the atmosphere that surrounds you. It is not just life, but also balance. The difference between a beautiful world like Earth, a world of alternating ice and fire like Mercury, or a hellscape like Venus, sometimes lies only in the colorless, odorless gas molecules we breathe every day. Why does each planet choose a different coat for itself? Why do some worlds lose that precious protection? The answer is related to their formation in the early days, to gravity, and even to terrible events in the past. At the end of this chapter, we have gained a general overview of the importance of the atmosphere. We understand that it is this coat that holds the key to controlling temperature, not just the distance to the Sunday, bareness and overload. These are the two extremes of a story about the evolution of planets. In the next chapter, we will return to our smallest neighbor to learn more. Why did Mercury become so bare? What stripped away its atmosphere, turning it into a planet of cold and hot extremes? Join me as we move on to Chapter 6 to decipher the harsh emptiness of Mercury. We have learned together about the importance of the atmospheric coat for a planet. Now, let your mind return to our smallest neighbor, lying silently and resiliently right next to the Sunday. Why has Mercury become so bare? Why couldn't it hold onto a layer of air to shield itself from the scorching sun and the biting cold? The story of Mercury's bareness is not just a lesson in physics, but also a sad song about the harshness of the universe. Imagine yourself standing on the surface of Mercury. There is no sound around you, because sound cannot travel in a vacuum. High above, the sky is always a deep black, even when the sun is shining brightly. There are no fluffy white clouds, no blue sky like on Earth. That emptiness is the clearest evidence of the absence of an atmosphere. There are three main reasons why Mercury lost its precious protection. The first reason lies in its own small body, its weak gravity. Imagine gravity as the hands of a mother trying to keep her children close. The children here are gas molecules like hydrogen, helium, or oxygen. The larger a planet is, the stronger its hands are, and it can hold many thick layers of gas around itself. But Mercury is too small. Its mass is only about 5.5% of Earth's mass. With such a modest frame, the gravitational pull on Mercury's surface is only about 38% of the gravity we feel every day. This means that Mercury's hands are too weak to hold onto gas molecules. They easily float up high and escape into the vastness of space, leaving the planet in solitude. The second reason comes from its giant and fiery neighbor, the Sun and its violent solar winds. A distance of 58 million kilometers may seem far, but to the Sun, it's within arm's reach. The Sun not only radiates light and heat, but it also constantly ejects streams of charged particles, moving at extremely high speeds, up to millions of kilometers per hour. We call that the solar wind. Imagine Mercury as a person trying to light a candle in the middle of a great storm. The solar windstorm sweeps past Mercury every second, every minute, without ever stopping. Any gas molecule that has just appeared on Mercury's surface, whether from chemical reactions or brought by meteorites, is immediately blown away by the solar wind. Mercury's efforts to form an atmosphere are like trying to build a sandcastle right at the edge of the sea. As soon as the waves come, the sand dissolves and washes back into the ocean. The third reason is the extremely high temperature. According to the laws of physics, when a gas is heated, its molecules move faster. At a temperature of 430 degrees Celsius on Mercury during the day, the gas molecules are like track and field athletes running at full speed. They move so fast that they exceed the planet's escape velocity. That is, the speed needed to escape the pull of gravity. When the gas molecules reach this speed, they will permanently leave the planet for deep space. The combination of weak gravity and high temperature created a terrible scenario. One side couldn't hold on, and the other always wanted to run away. It is this very lack of an atmosphere that has left heavy consequences on Mercury's appearance. Because there is no air to create friction and burn up space rocks, Mercury is completely defenseless against meteorites. Every small rock from space that hurtles towards it crashes directly onto the surface at tens of thousands of kilometers per hour, creating millions of impact craters of all sizes. NASA's Messenger mission, which orbited Mercury from 2011 to 2015, sent back astonishingly detailed images. Scientists saw that Mercury's surface looked like an ancient battlefield, where the scars never fade because there is no wind, no rain, and no atmosphere to erode or cover them. And most importantly, as we already know, this bareness is the reason why Mercury cannot retain heat. It receives a huge amount of thermal energy from the sun during the day, but because there is no atmospheric coat to trap the heat, all that energy escapes immediately when night falls. That's why the nights on Mercury are as cold as negative 180 degrees Celsius. It's like a bag with a hole in the bottom. No matter how much water you pour in, it will all flow out. The emptiness of Mercury reminds us of the fragility of the conditions necessary for balance. A planet can be very close to an energy source, but if it lacks protection and the ability to retain it, it will forever remain a world of harsh extremes. Closing this chapter, we now clearly understand why Mercury has no atmosphere and why it failed to become the hottest planet. Its bareness is a complete contrast to its next neighbor. While Mercury couldn't hold on to a single gas molecule, Venus hoards them frantically. In the next chapter, we will begin to uncover the true secret of Venus. We will learn about a concept that has turned it into a hellscape, the greenhouse effect. Join me as we step into the suffocating and scorching world of Venus to see how carbon dioxide has built a perfect heat trap. Now, let your mind temporarily leave the cold emptiness of Mercury to enter a completely opposite world. If Mercury is a naked wanderer under the sun, then Venus is a kingdom imprisoned within thick walls of air. In this chapter, we will decipher the real culprit that turned Venus into an eternal furnace, hotter than anywhere else in the solar system. That is the greenhouse effect, a phenomenon we often hear about on Earth, but on Venus, it has been pushed to a terrifying limit. To understand the greenhouse effect in the simplest way, imagine a car parked under the hot sun on a summer afternoon. Although the air outside might only be slightly muggy, the moment you open the car door, a blast of sweltering heat hits your face. Why is it so much hotter inside the car than outside? It's because the glass windows allowed sunlight to pass through easily, but trapped the heat, preventing it from escaping. Venus is just like that car, but instead of glass panels, it is enveloped by a layer of carbon dioxide that is thousands of layers thick. The atmosphere of Venus is a marvel of suffocation. While our Earth's atmosphere is mainly nitrogen and oxygen, the atmosphere of Venus is 96.5% carbon dioxide. This is a huge number. Carbon dioxide is a gas with a very special physical property. It is very friendly to light, but extremely picky with thermal energy. Imagine the light from the sun as small, gentle visitors, carrying energy in the form of short waves. These visitors easily penetrate the thick cloud layer of Venus to reach the rocky surface. When the planet's surface absorbs this light, it heats up and tries to radiate heat back into space to cool itself down. However, this radiated heat has now transformed into long waves, also known as infrared radiation. And this is when the trap begins to work. The dense carbon dioxide molecules in the atmosphere of Venus are like a diligent army of guards. They allow light to enter, but when the heat waves try to escape, they block the way, absorb that thermal energy, and then reflect it back to the planet's surface. And so, the thermal energy is trapped, bouncing back and forth between the ground and the sky with no way out. The result is that the temperature gradually accumulates, layer upon layer, until the entire planet becomes as scorching hot as a block of burning coal. Một điều thú vị và đầy nghịch lý là sao Kim thực tế phản xạ rất nhiều ánh sáng mặt trời nhờ lớp mây axit sulfuric trắng xóa bao phủ bên trên. Nó giống như một tấm gương khổng lồ phản chiếu tới 70% lượng ánh sáng nhận được quay trở lại vũ trụ. Điều này có nghĩa là lượng năng lượng thực sự xuyên qua được lớp mây để xuống tới mặt đất của sao Kim còn ít hơn cả lượng năng lượng mà trái đất nhận được. Thế nhưng, chỉ với một phần nhỏ năng lượng đó, nhờ vào cái bẫy khí carbonic hoàn hảo, sao Kim vẫn có thể duy trì mức nhiệt độ trung bình là 464 độ C. Các nhà khoa học gọi hiện tượng xảy ra trên sao Kim là hiệu ứng nhà kính mất kiểm soát. Trong quá khứ xa xôi, hàng tỷ năm trước, sao Kim có thể đã từng có những đại dương nước lỏng giống như trái đất, nhưng vì nằm gần mặt trời hơn, nhiệt độ bắt đầu tăng cao, khiến nước bốc hơi. Hơi nước cũng là một loại khí giữ nhiệt rất mạnh. Càng nhiều hơi nước bốc lên, hành tinh càng nóng hơn. Khi nhiệt độ đạt đến một ngưỡng nhất định, các đại dương bị đun sôi hoàn toàn. Sức nóng khủng khiếp sau đó đã giải phóng khí carbonic từ trong các lớp đá vôi vào bầu khí quyển, tạo nên một vòng lặp phản hồi tích cực, không thể dừng lại. Hành tinh càng nóng, khí giữ nhiệt càng nhiều. Khí càng nhiều, hành tinh lại càng nóng hơn. Ngày nay, sao Kim không còn một giọt nước nào. Nó khô cằn đến mức cực đoan. Toàn bộ lượng khí carbonic mà lẽ ra phải được lưu giữ trong lòng đá như ở trái đất thì nay đều nằm chém trệ trong bầu khí quyển, tạo nên một áp suất nặng nề đến mức không tưởng. Nếu bạn đứng trên bề mặt sao Kim, áp suất đó sẽ đè nặng lên cơ thể bạn, giống như khi bạn đang lặn sâu xuống 900 mét dưới đáy biển. Trong một môi trường vừa nóng bỏng vừa nặng nề như thế, mọi quy luật về sự sống mà chúng ta biết đều trở nên vô nghĩa. Hãy thử tưởng tượng về sự tĩnh lặng đáng sợ trong cái lò áp suất khổng lồ này. Không có gió nhẹ, không có mưa mát lành, chỉ có những luồng không khí đặc quánh khí carbonic đang âm thầm giữ chặt lấy từng hạt nhiệt từ mặt trời. Chính cơ chế giữ nhiệt tàn bạo này đã giúp sao Kim đánh bại sao Thủy trong cuộc đua về nhiệt độ. Sao Thủy có thể đứng gần nguồn nhiệt hơn, nhưng nó không có chiếc áo khoác kỳ diệu này để giữ lấy hơi ấm. Câu chuyện về hiệu ứng nhà kính trên sao Kim không chỉ là một kiến thức thiên văn xa xôi, nó giống như một tấm gương phản chiếu, nhắc nhở chúng ta về sự mong manh của bầu khí quyển trên chính hành tinh xanh của mình. Dù ở mức độ nhẹ nhàng hơn rất nhiều, nhưng cơ chế giữ nhiệt bởi khí carbonic vẫn đang vận hành mỗi ngày trên trái đất, giúp hành tinh của chúng ta đủ ấm để sự sống tồn tại. Tuy nhiên, bài học từ sao Kim cho thấy khi sự cân bằng bị phá vỡ, một thiên đường cũng có thể biến thành hỏa ngục. Khi bạn đang nằm đây, hít thở bầu không khí trong lành và cảm nhận hơi ấm vừa đủ của tấm trăng, hãy nhớ rằng ở cách chúng ta hàng triệu km, viên ngọc sáng sao Kim vẫn đang âm thầm bị nung nấu trong cái bẫy nhiệt của chính nó. Sự khác biệt giữa một giấc ngủ yên bình và một hỏa ngục đôi khi chỉ nằm ở thành phần của những phân tử khí không màu đang bao quanh hành tinh. Kết thúc chương này, chúng ta đã hiểu được tấm hành dinh của cái nóng trên sao Kim nằm ở đâu. Đó không phải là do khoảng cách, mà là do chính bầu khí quyển của nó. Nhưng khí quyển đó không chỉ có khí carbonic, nó còn chứa đựng những thành phần hóa học đầy thù nghịch khác, tạo nên một môi trường mà không một sinh vật nào có thể sống sót. Trong chương tiếp theo, chúng ta sẽ cùng nhau đi sâu vào chi tiết hơn về thành phần hóa học của sao Kim. Chúng ta sẽ tìm hiểu về những đám mây axit sulfuric và những cơn mưa không bao giờ chạm tới mặt đất. Hãy cùng tôi bước sang chương 8 để khám phá thế giới hóa học đầy khắc nghiệt của người chị em song sinh với trái đất. Hãy để tâm trí bạn tiếp tục bồng bềnh trong không gian mờ ảo của sao Kim, nơi mà mỗi hơi thở của hành tinh này đều mang theo những bí mật hóa học đầy khắc nghiệt. Nếu như ở chương trước, chúng ta đã biết về cái bẫy nhiệt khổng lồ được xây dựng từ khí carbonic, thì ở chương này, chúng ta sẽ cùng nhau đi sâu vào nhà bếp hóa học của sao Kim để xem những nguyên tố nào đã cùng nhau nhào nặn nên một thế giới thù nghịch đến thế. Bạn hãy tưởng tượng mình đang đứng trong một phòng thí nghiệm khổng lồ, nhưng thay vì những ống nghiệm thủy tinh, mọi thứ đều diễn ra trên quy mô của cả một hành tinh. Trên trái đất, bầu không khí mà chúng ta hít thở hàng ngày là một hỗn hợp dịu nhẹ với khoảng 78% là khí nitơ và 21% là khí oxy. Chính sự kết hợp này đã tạo nên sự sống, màu xanh của bầu trời và sự trong lành của những cơn mưa. Thế nhưng, trên sao Kim, bảng thành phần này đã bị đảo lộn hoàn toàn, tạo nên một hơi thở đặc quánh và độc hại. Thành phần chiếm ưu thế tuyệt đối trong bầu khí quyển sao Kim, như chúng ta đã nhắc tới, chính là khí carbonic. Nó chiếm tới 96,5% toàn bộ khối lượng không khí. Lượng khí carbonic khổng lồ này không chỉ giữ nhiệt mà còn tạo nên một áp lực đè nặng lên mọi thứ. Tuy nhiên, có một sự thật thú vị về khí nitơ trên hành tinh này. Mặc dù khí nitơ chỉ chiếm khoảng 3,5% bầu khí quyển sao Kim, nhưng vì bầu khí quyển của nó quá dày đặc và nặng nề, nên thực tế, tổng lượng khí nitơ trên sao Kim còn nhiều gấp 4 lần so với lượng khí nitơ trên trái đất của chúng ta. Điều này cho thấy quy mô khủng khiếp của chiếc áo khoác mà sao Kim đang khoác lên mình. Nhưng điều làm nên sự kinh hãi thực sự của sao Kim không chỉ là khí carbonic hay nitơ, mà chính là những thành phần chiếm tỷ lệ rất nhỏ nhưng đầy quyền năng khác. Đáng kể nhất là sự hiện diện của lưu huỳnh. Lưu huỳnh trên sao Kim không chỉ nằm dưới mặt đất trong những dòng nham thạch, mà nó còn bốc hơi và bay lơ lửng trong không trung khi các phân tử lưu huỳnh kết hợp với một lượng hơi nước ít ỏi còn sót lại và oxy dưới tác động của ánh sáng tia cực tím từ mặt trời. Chúng tạo thành những đám mây axit sulfuric dày đặc. Bạn hãy thử hình dung về những đám mây này. Chúng không phải là những đám mây trắng xốp, hiền hòa, mang theo mưa rào mát rượi. Đó là những dải mây màu vàng nhạt, bao phủ toàn bộ hành tinh và vĩnh viễn không bao giờ tan biến. Những giọt axit sulfuric nhỏ li ti này có tính ăn mòn cực mạnh. Nếu một con tàu vũ trụ của con người lướt qua những tầng mây này mà không có lớp bảo vệ đặc biệt, nó sẽ bị hủy hoại chỉ trong tích tắc. Chính lớp mây axit sulfuric này là tấm rèm ngăn cản chúng ta nhìn thấy bề mặt hành tinh bằng mắt thường. Đồng thời, nó cũng phản xạ ánh sáng mặt trời, tạo nên vẻ rực rỡ lừa dối khi nhìn từ trái đất. Một trong những hiện tượng hóa học kỳ lạ và buồn bã nhất trên sao Kim chính là những cơn mưa. Ở những tầng mây cao, axit sulfuric có thể ngưng tụ và rơi xuống giống như mưa trên trái đất. Thế nhưng, những hạt mưa axit này không bao giờ có cơ hội chạm tới mặt đất. Khi chúng rơi xuống tầng thấp hơn, nơi nhiệt độ bắt đầu tăng cao khủng khiếp, những giọt axit này bị đun nóng và bốc hơi ngược trở lại bầu trời trước khi kịp rơi xuống những hòn đá núi lửa. Các nhà khoa học gọi hiện tượng này là mưa Maviga. Hãy tưởng tượng một thế giới nơi những cơn mưa vĩnh viễn bị treo lơ lửng giữa không trung, một sự khao khát cái mát lành không bao giờ được hồi đáp. Bên cạnh lưu huỳnh và axit sulfuric, bầu khí quyển sao Kim còn chứa một lượng nhỏ các khí khác như khí argon, heli và neon. Tuy nhiên, sự thiếu vắng quan trọng nhất chính là nước. Nếu chúng ta gom toàn bộ hơi nước trong bầu khí quyển sao Kim lại và trải đều trên bề mặt hành tinh, nó chỉ tạo thành một lớp nước mỏng dày khoảng 3 cm. Để so sánh, nếu làm điều tương tự với trái đất, chúng ta sẽ có một đại dương toàn cầu sâu tới 3.000 mét. Sao Kim là một thế giới bị tước đoạt nước một cách triệt để nhất trong hệ mặt trời. Các phân tử nước trong quá khứ đã bị nhiệt độ cao bé gáy thành hydro và oxy. Hydro nhẹ hơn nên đã bay mất vào không gian, còn oxy thì bị nhốt lại trong các phản ứng hóa học với các kim loại trên bề mặt đá. Màu sắc của bầu trời sao Kim cũng là một sản phẩm của hóa học. Nếu bạn có thể đứng trên bề mặt hành tinh mà không bị sức nóng nung chảy, bạn sẽ thấy bầu trời không có màu xanh mà mang một sắc cam mờ đục hoặc đỏ sẫm. Đó là kết quả của hiện tượng tán xạ ánh sáng qua lớp khí carbonic cực dày và sự hiện diện của bụi lưu huỳnh. Ánh sáng mặt trời sau khi lọc qua những tầng mây axit và bầu không khí đặc quánh chỉ còn lại những tông màu nóng, tạo nên một cảm giác ngột ngạt và nhuốm màu tàn tích. The origin of Venus's abundant sulfur is still a topic of debate, but the leading hypothesis is intense volcanic activity. Venus has more volcanoes than any other planet in the solar system. Relentless eruptions over billions of years have pumped massive amounts of sulfur gas into the atmosphere. With no oceans to absorb it and no geological cycles to bury the sulfur underground like on Earth, these gases just accumulated, turning the atmosphere into a dense and deadly chemical soup. When we study the chemistry of Venus, we realize that everything here is tightly interconnected. Carbon dioxide traps heat, the high temperature causes water to evaporate and disappear, the lack of water prevents the absorption of toxic gases, and volcanoes continue to add more hostile chemicals. It's a closed system, an inescapable feedback loop that has turned Earth's sister into a place inhospitable to life. This precious data didn't just appear out of nowhere. It's the result of courageous missions. NASA's Pioneer Venus and the Soviet Union's Venera probes had to sacrifice themselves, plunging into that dense atmosphere to take chemical measurements before being utterly destroyed. Thanks to them, we learned that behind Venus's sparkling, diamond-like beauty lies the overpowering stench of rotten eggs, characteristic of sulfur and the presence of the most potent acids. Let your mind rest in the understanding of the universe's diversity. We are so fortunate to live on a planet where chemical elements combine harmoniously to create fresh air, cool water, and blue skies. The harshness of Venus is a reminder of the miraculous balance we enjoy. As we conclude this chapter, we have formed a clear picture of the breath of Venus, a mixture of carbon dioxide, nitrogen, and sulfuric acid. But that atmosphere doesn't just cause heat and toxicity. It also creates an immense physical pressure that no living creature could possibly imagine. In the next chapter, we will explore the surface pressure of Venus. We'll discover what it feels like to be crushed by hundreds of layers of atmosphere and why this pressure plays a crucial role in maintaining the planet's record-breaking temperatures. Join me as we turn to Chapter 9 to experience the suffocating pressure of this fiery kingdom. Let your mind continue to drift into the hazy, dense atmosphere of Venus. Having passed through the pale yellow acid clouds and understood this planet's carbon dioxide-filled breath, we will now explore another aspect just as terrifying as the heat. That is the pressure. If the temperature is a scorching fire, then the pressure is a giant hand crushing everything on the surface of Earth's twin sister. Close your eyes and imagine you're standing on a beautiful beach on a breezy afternoon. The air around us feels weightless. We walk, run, and breathe easily without feeling any pressure at all. And yet, the reality is that Earth's atmosphere is pressing down on every square inch of our bodies with a force of about 14.7 pounds. We don't feel it because the human body has evolved to balance this pressure from the inside. Now, imagine you're diving deep into the ocean. The deeper you go, the more your ears begin to hurt and your chest feels compressed. That's because of the immense weight of the water column above you pressing down. When you reach a depth of about 3,000 feet, that pressure becomes terrifying, enough to crush any structure that isn't sufficiently reinforced. And that is what it feels like to stand on the surface of Venus. The pressure on the surface of Venus is about 92 times greater than the pressure at sea level on Earth. To help you visualize this, if you were standing there, the pressure of the atmosphere on your body would be equivalent to having a fully loaded truck resting on each of your fingertips. This is an unimaginable figure for a rocky planet. How can an atmosphere, which is just made of colorless gas molecules, be so heavy? The answer lies in the immense mass of Venus's atmosphere. As we know, this atmospheric cloak is mostly carbon dioxide, and it is incredibly dense. The total mass of Venus's atmosphere is about 90 times greater than that of Earth's. Because Venus's gravity is nearly the same as Earth's, this entire mass of gas is pulled down and tightly compressed onto the planet's surface, creating a dense ocean of air at 464 degrees Celsius, and this extreme pressure, carbon dioxide, no longer behaves like the normal gas we see in the bubbles of a soft drink. It enters a strange state that scientists call a supercritical fluid. In this state, the carbon dioxide has properties of both a gas and a liquid. It can seep through openings like a gas, but has the density and crushing power of a liquid. Imagine walking through a swimming pool filled with hot molasses. Every movement would be slow and laborious. The winds on the surface of Venus move at only a few miles per hour, much slower than the high-altitude winds, but because the air is so dense, they carry tremendous force. A gentle breeze on Venus could knock over an adult, just like a raging flood current on Earth. This suffocating pressure is the greatest challenge for engineers designing exploratory probes. In the history of space exploration, the Soviet Union's Venera series of spacecraft had to be built like specialized submarines, designed to dive to the deepest ocean trenches. They were made from ultra-durable alloys, with thick hulls and a spherical structure to distribute the immense pressure evenly. In 1970, when the Venera 7 lander touched down, it had to withstand pressure 90 times that of Earth's, along with scorching heat. The craft was heavily damaged upon landing and was only able to transmit signals for a mere 23 minutes. Subsequent landers, though more robust, survived for only about 1 to 2 hours before their electronics melted and their structures were crushed by the pressure. So, how is pressure related to Venus's record-high temperatures? In physics, pressure and temperature often go hand in hand. When you compress a gas into a small space, its molecules collide more frequently, generating heat. You can see this when you pump up a bicycle tire. The pump gets hot after you've been compressing air. On Venus, the immense weight of the atmosphere pressing down also contributes to raising the temperature of the air near the surface. Furthermore, this dense atmosphere acts like an incredibly thick blanket. It not only traps heat from the greenhouse effect, but also prevents that thermal energy from escaping more effectively than anything else. The combination of a chemical trap, the carbon dioxide, and a physical trap, the pressure and density, has turned Venus into a giant pressure cooker with no release valve. In the quiet, hazy stillness of this fiery kingdom, time seems to stand still under the suffocating pressure. No creature from Earth could survive these harsh conditions, not even for a single second. Even the rocks on the surface of Venus have been transformed by the effects of pressure and heat over billions of years. As you lie here, feeling the lightness of the air with every breath, cherish the freedom that Earth's atmosphere provides. We are not crushed, not suffocated. We are enveloped by a layer of gas, just thick enough to protect us, yet light enough to let us feel free. The difference in pressure between Mercury and Venus is further proof of why the second planet is hotter than the first. Mercury has nothing pressing down, nothing to trap heat. It is essentially a vacuum. Venus, on the other hand, has far too much in abundance so extreme it has become hostile. As we end this chapter, we now understand the invisible but terrifying weight of Venus. This pressure, combined with the greenhouse effect and toxic chemical composition, completes the picture of the solar system's hell. But have these two planets always been this way since their birth? Or did some cataclysmic event occur that changed their fates? In the next chapter, we will travel back in time to learn about the evolution of Mercury and Venus. We will explore the distant past, when Venus might have once been a blue paradise like Earth before becoming the furnace it is today. Join me as we turn to Chapter 10 to hear the story of how time can change everything. Let your mind continue to drift on the flow of time, an invisible river carrying us back to the distant past, when the solar system was just a newborn. In the stillness of tonight, we will uncover a great secret. Our two neighbors, Mercury and Venus, were not always as harsh as we see them today. There was an age, billions of years ago, when their stories might have taken a completely different turn. We begin our journey back in time to about 4.5 billion years ago. Back then, the sun had just formed from a giant cloud of dust and gas. Around it, the planets were also beginning to take shape from colliding debris. During this chaotic, primordial stage, both Mercury and Venus held immense potential. First, let's look at Mercury. As we know, today the planet is like a burnt-out cinder, but in the past, it may have been much larger. Scientists believe that about 4 billion years ago, Mercury experienced a horrific cataclysm. Another small planet, perhaps about 1/6 the size of Earth, slammed into Mercury at an incredible speed. This collision was so catastrophic that it blasted most of Mercury's rocky crust and outer mantle into space. What remained after that cosmic bombardment is the giant iron core we see today, making up 3/4 of the planet's radius. From a planet with the potential to have an atmosphere and a complex structure, Mercury was whittled down into a bare metallic sphere, pushed closer to the sun, and permanently lost its chance to hold on to any protective atmosphere. From that moment on, Mercury's fate was sealed. It became a loyal but harsh gatekeeper, bearing the full wrath of its parent star. But the most astonishing story lies with Venus. If you could turn back time about 2 billion years, you probably wouldn't recognize this twin sister. According to the most advanced computer simulations from scientists at NASA, Venus in the past might have been a blue paradise. At that time, the sun was younger and about 30% dimmer than it is today. With a gentler sun, Venus could have had a remarkably temperate surface temperature. Imagine a Venus with vast oceans of liquid water, cool breezes blowing across rocky continents, and a sky that might have been as blue as Earth's. Chemical evidence from measuring the ratio between heavy and light forms of hydrogen gas, known as deuterium, and regular hydrogen in Venus's current atmosphere suggests the planet once had a colossal amount of water, enough to cover its entire surface in an ocean hundreds of meters deep. For at least 2 billion years, Venus may have maintained these conditions a period long enough for life to have possibly sprouted and evolved. So, what turned this paradise into a hellscape? The answer lies in the slow but irreversible change of the sun itself. Every billion years, the sun gets about 10% hotter and brighter. For Venus, already on the inner edge of the habitable zone, this temperature increase was the trigger for a catastrophic chain reaction. As the temperature began to rise, the oceans on Venus started to evaporate more rapidly. Water vapor rose into the atmosphere, and as we know, water vapor is an extremely potent heat-trapping gas. The more water vapor rose, the more heat the atmosphere retained from the sunday. This created a devastating positive feedback loop. Rising temperatures caused more water to evaporate, and more water vapor caused the temperature to rise even higher. At a tipping point, the temperature on Venus became so hot that the oceans boiled away completely. All the water turned to vapor, creating an extreme heat-trapping atmosphere. In the upper layers of the atmosphere, water molecules were broken apart into hydrogen and oxygen atoms by the sun's ultraviolet light. Hydrogen, the lightest element in the universe, quickly escaped the planet's weak gravity and fled into deep space. Venus permanently lost its precious water, but the tragedy didn't stop there. On Earth, water plays a crucial role in operating plate tectonics and helping to dissolve carbon dioxide from the atmosphere into oceans and limestone. When the water on Venus disappeared, this carbon dioxide cleanup mechanism also ceased to function. Relentless volcanic activity pumped enormous amounts of carbon dioxide into the air, but there was no longer any water to absorb it back into the ground. Carbon dioxide accumulated, becoming denser and denser, replacing the lost water vapor and establishing the permanent greenhouse effect we see today. Venus and Earth began their journeys from nearly identical starting points, but just because of a small difference in their distance from the Sun, their evolutionary paths diverged in opposite directions. Earth was lucky enough to be in a just right position to retain its liquid water, maintain its carbon cycle, and protect life. Meanwhile, Venus was pushed past the boundary of equilibrium and fell into an irreversible state. This story of evolution teaches us that planets are not static entities. They are living systems, constantly changing and deeply influenced by their surroundings. The barrenness of Mercury after its ancient collision and the scorching heat of Venus after losing its oceans are powerful testaments to the harshness of time and space. As you lie here, try to feel the magic of every drop of water and every breath of fresh air on Earth. They are the result of billions of years of delicate balance, a stroke of luck that our neighbors did not have. Mercury lost its crust, Venus lost its oceans, and only we are left to cherish these treasures in the embrace of the cosmos. We have now understood the turbulent past of these two planets, but their harshness comes not only from within, but also from the relentless impacts from outer space. In the next chapter, we will learn about an invisible but incredibly powerful force, the solar wind. We will see how these streams of charged particles have eroded and shaped the fate of Mercury. Let your mind continue to drift along the invisible streams of energy weaving through the solar system. After journeying back in time together to learn about the turbulent past of our two neighbors, we will return to the present to face a powerful force. This is a wind that carries no ocean moisture, no rustling of leaves, but a stream of hot and powerful charged particles. We call it the solar wind. In this chapter, we will learn how this stream has relentlessly eroded and shaped the barren fate of Mercury, contributing to the paradoxical temperature difference with Venus. Imagine the Sun is not just a stationary ball of fire shining brightly. In reality, it is a colossal and incredibly turbulent nuclear reactor. From its outer corona, tiny particles like protons and electrons are continuously ejected into space at tremendous speeds, from 300,000 to 800,000 kilometers per hour. This stream of particles radiates in all directions, creating a perpetual storm that sweeps across all the planets. For Mercury, the planet closest to the Sun, at a distance of 58 million kilometers, this stream is like a direct hurricane. Imagine Mercury as a small stone placed right in front of the mouth of a giant industrial fan, running at full power. At such a close distance, the density and energy of the solar wind hitting Mercury are many times stronger than when they reach Earth or Venus. One of the reasons Mercury is so ravaged by the solar wind is its lack of a strong enough protective shield. Here on Earth, we have a very strong magnetic field that forms an invisible cocoon around the planet, helping to deflect harmful charged particles from the sunday. However, Mercury is not so fortunate. Despite having a huge iron core, because the planet rotates so slowly, the magnetic field it generates is incredibly weak, only about 1% as strong as Earth's. Because of this flimsy shield, the solar wind can easily penetrate and reach Mercury's surface. When these highly charged particles slam down, they perform a process scientists call space weathering. Imagine these tiny particles as microscopic bullets, constantly bombarding the planet's rocky surface. The impact is so powerful that it can knock atoms right off the rock, turning them into suspended gases. This is the origin of the thin exosphere we mentioned in previous chapters. Elements like sodium, potassium, and calcium are stolen from the rocky crust by the solar wind and pushed into the air. But the tragedy is that as soon as these atoms escape, the very same solar wind continues to push them further away, sweeping them into deep space. Mercury is like someone trying to make a blanket out of sand in the middle of a storm. Wherever the wind blows, the sand goes with it. NASA's Messenger spacecraft mission has provided us with invaluable data on this process. The craft observed a long tail behind Mercury, resembling the tail of a comet. This tail is actually composed of sodium atoms and other gas particles being blown away from the planet by the solar wind. This shows that erosion is happening daily, hourly, turning Mercury into an entity that can never accumulate a true atmosphere. And this is the crucial link in explaining why Mercury is colder than Venus. Because the solar wind is too strong and its magnetic field too weak, Mercury has no way to retain heat-trapping gases like carbon dioxide. With no heat-trapping gas and no atmosphere, Mercury is incapable of a greenhouse effect. All the thermal energy it receives from the sun during the day is stripped away by the solar wind and the vacuum of space. Meanwhile, let's look at Venus. Although it's also affected by the solar wind, Venus is farther away, so the wind's intensity is significantly reduced. Furthermore, even though Venus doesn't have a strong intrinsic magnetic field like Earth, its extremely dense atmosphere interacts with the solar wind to create a kind of induced magnetic field. This magnetic field, combined with the incredible thickness of its atmosphere, has helped Venus hold onto its coat much more tenaciously. The carbon dioxide on Venus isn't easily blown away like on Mercury, allowing it to build the perfect heat trap that we know today. Space weathering also leaves its mark on the color and rock structure of Mercury. The microscopic dust particles on the planet's surface are chemically altered by the impact of charged particles, causing its surface to become dark and gray. When we look at the images sent back by probes, we see a world of erosion, a testament to the destructive power of the stellar wind. In the silence of deep space, picture this unbalanced fight. On one side, a tiny planet struggles to hold itself together. On the other, the fiery breath of the sun blows relentlessly. This invisible wind is what robs Mercury of its chance to stay warm through the night, leaving it in a harsh state of scorching heat, alternating with freezing cold. Astronomy isn't just about twinkling stars. It's also about the powerful forces silently shaping the universe. Space weathering on Mercury helps us understand that to maintain a stable environment, a planet needs more than just a good location. It needs a protective mechanism, a shield to fend off the storms from its own parent star. We'll end our story about the solar wind here. You now understand another reason why Mercury can never be the hottest planet. But humans didn't discover these secrets by chance. It was thanks to the intelligence and courage of great minds on Earth and the sophisticated machines they launched into space. In the next chapter, we'll look back at the visits from Earth. We'll learn about the heroic spacecraft that braved the dangers to reach Mercury and Venus, giving us the priceless images and data we have today. Join me as we turn to Chapter 12 to talk about the missions that conquered the darkness. Let your mind continue to float in the silence of space, where distant stars shine steadfastly. Now that we understand the invisible forces like the solar wind and the evolution over billions of years, let's turn to a different story, one of humanity and courage. It's the story of Steel Envoys, the small spacecraft that humanity sent from our blue planet to touch the mysteries of Mercury and Venus. In this chapter, we'll revisit the key milestones, the difficult journeys that helped us solve the paradox of heat in our solar system. Picture the 1960s, when humanity was just taking its first fledgling steps into the vastness of space. With an infinite thirst for knowledge, we weren't content with just looking through telescopes. We wanted to send our eyes right to the source. The first and most enticing target was Venus, the brilliant planet often visible at dusk. The quest to conquer Venus is one of the most epic chapters in the history of astronomy. The pioneers in reaching this planet's surface were Soviet scientists with their Venera program. Picture spacecraft that were built to be incredibly tough, resembling giant pressure cookers or submarines designed for the deepest parts of the ocean. Because to survive on Venus, a probe had to withstand not only the heat, but also a crushing pressure. In 1967, the Venera 4 probe entered Venus's atmosphere. It was the first device to send back direct data, confirming that the atmosphere here contains over 90% carbon dioxide. However, the planet's terrifying pressure crushed the probe before it could reach the ground. It wasn't until 1970 that the Venera 7 probe truly made history by becoming the first man-made object to successfully land and send a signal from the surface of another planet back to Earth. It only survived for a mere 23 minutes in the 470-degree Celsius heat. But those were 23 priceless minutes, telling us exactly how harsh this hell truly was. Following the Soviet Union, the American Space Agency, known as NASA, also sent important missions. The Pioneer Venus probe in the late 70s conducted a comprehensive survey from above, helping us better understand the structure of the dense sulfuric acid cloud layers. But perhaps the most impressive was the Magellan mission in 1990. Since Venus's clouds are too thick for visible light to pass through, the Magellan probe used radar to see through the haze. The craft created a detailed map of most of Venus's surface, revealing a world full of volcanoes, cooled lava flows, and towering cliffs. It was thanks to Magellan that we learned Venus's surface is geologically very young, indicating the planet once had extremely intense internal activity. While exploring Venus was like a battle against heat and pressure, approaching Mercury was a challenge of speed and gravity. Imagine, sending a probe to Mercury is like trying to throw a marble close to a raging fire without it being sucked straight into the heart of the flame. The sun's enormous gravity is always waiting to swallow anything that gets too close. The first mission to Mercury was NASA's Mariner 10 in 1974. To save fuel, scientists used an incredibly clever technique. They used the gravity of Venus to propel the spacecraft toward Mercury. Mariner 10 flew by Mercury 3 times, sending back the first black and white photos of a world full of impact craters, looking very much like our own moon. This flyby revealed Mercury's barren nature and confirmed it has virtually no atmosphere. It took more than 30 years for us to return to this tiny neighbor with NASA's Messenger mission, launched in 2004. This was the first spacecraft to actually enter orbit around Mercury instead of just flying past. During 4 years of hard work from 2011 to 2015, Messenger provided an astonishingly comprehensive view. It discovered that Mercury has an unusually large iron core, confirmed the existence of water ice in permanently shadowed craters at the poles, and observed how the solar wind continuously erodes the planet. These spacecraft, whether Venera, Mariner, or Messenger, all carried sophisticated instruments, digital cameras, spectrometers to analyze chemical composition, and extremely accurate temperature sensors. Thanks to them, we no longer have to guess why Venus is hotter than Mercury. We now have specific numbers on the carbon dioxide concentration, the pressure 92 times that of Earth on Venus, and the near total vacuum on Mercury. Most recently, a joint European and Japanese mission named Bepi Colombo is on its way to Mercury. It is expected to enter orbit around 2025, promising to bring new discoveries about the planet's internal structure and weak magnetic field. As you lie here, in the safety of your home, Try to imagine those tiny pieces of steel, lonely in the vastness of space. Some spacecraft have melted on the surface of Venus. Others have run out of energy and lie forever on the rocky plains of Mercury. They are memorials to human intellect and curiosity. Every photo, every line of data they sent back has helped us better understand our place in the universe, the fragility of life, and the wonder of the laws of physics. These visits from Earth have taught us that no matter how harsh the universe may be, we can still use our intelligence to reach out and understand it. The difference between the heat of Venus and the cold of Mercury is no longer a mystery, but a clear scientific lesson written by these heroic missions. As we conclude this chapter, we've paid tribute to these space envoys. We have learned how humans managed to gather that precious knowledge. But beyond distance, atmosphere, or solar wind, there is another factor that also contributes to the distribution of heat energy on these planets. That is, the rhythm of time, the way they rotate on their own axes. In the next chapter, we will learn about the long days and long nights on Mercury and Venus. We will see how their slow rotation has affected a planet's heat and why time here is so different from on Earth. Join me as we turn to chapter 13 to discover the slow pulse of these fiery worlds. In the endless silence of the universe, time does not pass in the way we usually perceive it on Earth. On our blue planet, a day and a night pass in just 24 short hours, a rhythm perfectly suited for us to work, rest, and fall asleep. However, upon entering the realm of Mercury and Venus, the beat of time becomes astonishingly slow. It is this slow rotation that has contributed significantly to creating the bizarre temperature characteristics we are now exploring. Let's begin with Mercury, the small planet named after the swift messenger god. There is an interesting paradox here. Mercury orbits the Sun very quickly, but rotates on its axis extremely slowly. It only takes 88 Earth days to complete one orbit, but it takes 59 Earth days to complete one rotation on its axis. This strange combination, along with the strong influence of the Sun's gravity, has created a rare phenomenon. A solar day on Mercury, that is, the time from one sunrise to the next, lasts for 100 to 76 Earth days. Just imagine standing on the parched surface of Mercury. A single morning here lasts for a grueling 88 of our days. During that entire, lengthy period, the sun hangs menacingly in the sky, relentlessly pouring down scorching showers of radiation. With no atmosphere to distribute the heat, the rocky surface below is continuously baked, day after day, until the temperature reaches a staggering 430 degrees Celsius. Then, when night finally falls, it too lasts for 88 Earth days. There are no winds to carry warmth from the other side of the planet, and no atmospheric blanket to retain heat. So all the heat accumulated during the day radiates straight out into the void. In that deep and prolonged darkness, the biting cold of space begins to take hold, causing the temperature to plummet to negative 180 degrees Celsius. Mercury is like someone lying on an intensely hot heating pad and then being instantly thrown into a perpetual freezer. The slowness of time amplifies these extremes to their maximum. Now, let's leave the gray, cratered surface of Mercury and fly to Venus. If time on Mercury was strange, on Venus, it defies all conventional logic. Venus is a true rebel in the solar system. While most planets rotate from west to east, Venus spins backward, from east to west. Not only does it spin in reverse, but it also rotates at an incredibly slow pace. It takes 243 Earth days for it to complete one rotation on its axis, while it only takes 225 days to orbit the Sun day. This means a single day here is longer than an entire year. However, due to its retrograde rotation and orbital motion, a solar day on Venus actually lasts about 117 Earth days. That's more than enough time to cook anything without shelter. But this is where the magic of Venus's atmosphere comes into play. Although the planet itself rotates very slowly, its dense atmosphere is anything but still. There's a phenomenon scientists call superrotation. The sulfuric acid clouds in Venus's upper atmosphere move at incredible speeds, up to 360 kilometers per hour. This is 60 times faster than the rotation speed of the planet's surface below. Imagine thick streams of carbon dioxide swirling like great rivers in the sky, circling the entire planet in just 4 Earth days. This superrotation acts as a colossal heat circulation system. The powerful winds carry heat from the day side to the night side, and from the scorching equatorial region to the 2 colder polar regions. Thanks to this continuous and tireless atmospheric circulation, Venus never has to endure a frigid night like Mercury's. Even when the sun sets, that thick atmospheric blanket and its swift winds keep the entire planet at a uniform temperature of 464 degrees Celsius. The difference between night and day on Venus is almost non-existent in terms of temperature. Whether you're in a place receiving direct sunlight or one submerged in the dense darkness of midnight, the scorching heat and crushing pressure feel exactly the same. This is a terrifying temperature stability, turning the entire planet into a giant, relentlessly operating pressure cooker. When we look at the rhythm of time on these 2 worlds, we see 2 different fates. On Mercury, the slow rotation, combined with the emptiness of space, has created a world of irreconcilable extremes. There, time is the enemy, endlessly prolonging the agony of searing heat and bone-chilling cold. In contrast, on Venus, the atmosphere has triumphed over the slowness of time. The super-rotating winds have turned the planet's sluggish pace into an incredibly efficient global heating system. The slowness of Venus and Mercury also reminds us of the power of gravity. Both are located too close to the Sun, and the immense gravitational pull of their parent star has acted on their rotations over billions of years, like a giant hand hitting the brakes, slowing down the spin of these planets. Let your mind relax completely in the understanding of these long days and endless nights in space. There, a sunset can last for weeks, and the dawn is as leisurely as a never-ending dream. In the quiet of the night on Earth, our own 24-hour rhythm suddenly feels so precious and gentle. Concluding this chapter, we've understood another crucial piece of the puzzle: why the temperature on Mercury fluctuates so violently while Venus remains consistently scorching hot. It's the combination of the rhythm of time and the power of the atmosphere. But the story of Venus isn't just about distant astronomy. It also carries a critical warning for our own planet. In the next chapter, we will reflect on the lessons Venus sends to Earth. We will learn how studying this hot sister helps us better understand climate change and the future of our own green home. Join me as we turn to chapter 14 to listen to this whisper from the cosmos. Let your mind continue to drift in the vast silence of the universe. After traversing the scorched lands of Mercury, passing through the dense acid clouds of Venus, and understanding the slow rhythm of time, let us now make a journey back. Looking back from Venus's orbit, our Earth appears as a magical blue marble, brilliant and full of life amidst the immense darkness. In this chapter, we will reflect on the precious lessons that our hot sister, Venus, has sent to our shared home. The story of Venus is not just a piece of distant astronomical knowledge. It is also a mirror reflecting Earth's own future. Imagine Earth and Venus as twin sisters who grew up together in the same home, the solar system. They have the same size, the same mass, and were formed from the same initial materials. Yet, while one sister became a paradise for millions of species, the other took a turn into a suffocating inferno. Why is there such a devastating difference? And could Earth ever repeat Venus's fate? The first and most important lesson Venus teaches us is about the power of atmospheric balance. As we know, The greenhouse effect isn't entirely a bad thing. On Earth, without a small amount of carbon dioxide and water vapor to retain heat, our planet would become an ice ball with an average temperature of about -18 degrees Celsius. Life would have never had a chance to blossom. However, Venus is a testament to what happens when this balance is completely shattered. When the concentration of carbon dioxide becomes too high, it's no longer a warm blanket, but becomes a death trap. Scientists on Earth began to really pay attention to climate change precisely from studying Venus. Did you know that James Hansen, one of NASA's pioneering climate change scientists, began his career by trying to understand why Venus was so hot? The mathematical and physical models he used to decipher Venus's atmosphere were later applied to predict the future of Earth's atmosphere. Venus is the giant laboratory that allows us to foresee the scenario of a planet with runaway temperatures. Another profound lesson is the role of oceans. On Earth, liquid water is not only the source of life, but also a silent hero in regulating the climate. Our oceans absorb a massive amount of carbon dioxide from the atmosphere, then convert it into sedimentary rocks at the bottom of the sea through geological cycles that last millions of years. Venus may have once had oceans like these in its past, but when the temperature rose beyond a threshold, the water completely evaporated, and the planet lost its natural carbon dioxide filter. Once the water was gone, the path back to life was almost completely sealed off. This reminds us of the fragility of the habitable zone. This is a band of space around the sun, where the temperature is just right for water to exist in liquid form. Venus sits on the inner edge of this zone, while Earth is situated more centrally. A distance of just a few tens of millions of kilometers creates the difference between a place of flowing water and one of molten rock. We realize that the boundary between a living planet and a dead one is incredibly thin. A small change in atmospheric composition or the sun's intensity could push a world past its tipping point. Let's consider the concentration of carbon dioxide on Earth today. Although it makes up only about 0.04% of the atmosphere, this number has increased significantly since the pre-industrial era. Venus teaches us about the concept of a positive feedback loop. This is when a small change leads to a larger change, which in turn accelerates the process even further. On Venus, rising temperatures vaporized water, which trapped more heat, causing temperatures to rise further, a loop that couldn't stop until everything was scorched. This lesson urges us to cherish and protect our current balance, and not let Earth stray too far into similar, dangerous loops. Besides that, Venus also teaches us about the value of observation and prediction. Thanks to spacecraft like the Soviet Union's Venera series or America's Magellan, we've come to understand that geology and atmosphere are deeply connected. The giant volcanoes on Venus pumped carbon dioxide into the air, but there were no biological processes to reclaim it. Our Earth has forests, oceans, and life to participate in this cycle. Life is not just an inhabitant on the planet. Life itself is a crucial part of keeping the planet cool and stable. As you lie here, feeling your steady breath and the gentle warmth from your blankets and pillows, think about our great fortune. We live on a planet with a perfect jacket not too thin like Mercury's, which suffers from alternating ice and fire, and not too thick like Venus's, which suffocates in a furnace. Every green forest, every cool river, and every gentle breeze is the result of a miraculous balance that the universe has bestowed upon us. Studying Venus is not meant to make us fearful, but to help us love and protect the Earth more. It helps us realize that in this vast universe, a green and vibrant home is incredibly rare and precious. The lessons from the sky help us reflect on our actions here on the ground to ensure that Earth will forever maintain its magnificent and gentle beauty for all generations to come. As this chapter closes, your mind is likely filled with gratitude for life and the delicate balance of nature. We've understood why Venus is so hot, and we've also understood the value of learning from our distant neighbors. The story of these two planets has come to its scientific conclusion, but the feelings and awe they inspire will linger on. In the final chapter, Chapter 15, we will recap this entire journey together. We will spend these last moments soaring among the stars, listening to the breath of the cosmos, and finding absolute peace before sinking into a very deep sleep. Please join me as we move to the final chapter to complete this wondrous journey. Welcome to the final leg of our journey. After traveling through 14 chapters filled with knowledge about the stars, fiery planets, and cold, empty spaces, it is now time for us to rest together. Allow yourself to truly let go. Adjust your pillow until it's perfectly comfortable. Pull the warm blanket up to your chest and feel the absolute silence enveloping the room. In this final chapter, I won't bring you new numbers or complex theories. Instead, we will reflect on the beauty of the universe and find peace in our souls before drifting off into a deep sleep. Our journey began with a simple yet fascinating riddle. Why is Venus hotter than Mercury, even though it's farther from the Sun? We flew together to the edge of the Sun to visit Mercury, the child of the messenger god. We saw a tiny, barren planet covered in impact scars. Mercury is like a wanderer, standing right next to a giant fire, but without a single coat to wear. Lacking an atmosphere, Mercury receives an enormous amount of heat during the day, but loses it all as soon as night falls. It is a world of solitude and harsh extremes, where the heat of 430 degrees Celsius and the cold of negative 180 degrees Celsius take turns reigning. Then, we glided together across millions and millions of kilometers to reach Venus, a planet with the magnificent beauty of a goddess of love, yet hiding a blazing heart. We discovered that its thick coat of carbon dioxide made all the difference. Venus doesn't need to be too close to the sun to be the hottest place. It just needs to know how to retain heat. With its extreme greenhouse effect, the heavy atmosphere has turned Venus into a heat trap with no escape, maintaining a stable temperature of 464 degrees Celsius day and night. We have understood that in the vast universe, distance is sometimes not as important as protection. Mercury is closer, but empty. Venus is farther, but overwhelmingly suffocating. The difference between these two worlds is a lesson in balance, something we are incredibly fortunate to have here on Earth. Now, imagine yourself standing in a place very far away, looking back at our solar system. From this distance, all arguments about temperature or pressure fade away. All the hostility of acid clouds or the violence of solar winds becomes tiny before the vastness of space. You see the sun shining gently like a lamp in the dark night. You see Mercury as a tiny grain of sand and Venus as a brilliant gem. Our universe is a symphony full of rhythm. There is the rhythm of rotation on an axis, the rhythm of orbits, and the rhythm of evolution over billions of years. Each planet has its own story, its own destiny, and an irreplaceable place. We, the tiny humans on this blue planet, have spent centuries exploring and understanding those stories. And that understanding brings us a strange sense of peace, because when we understand the universe, we realize that we are part of a grand, precise, and artistic system. Take a deep breath and exhale very slowly. Feel the heaviness of your eyelids, the softness of your body sinking deeper into the mattress. The information about carbon dioxide, sulfuric acid, or the 92 times greater pressure on Venus are now just faint memories, drifting farther and farther away into the darkness. You no longer need to think or analyze anything. All mysteries have been solved. All curiosities have been satisfied. Let your mind drift freely among the galaxies of the Milky Way. You are gliding past colorful nebulae, past newly formed stars, sparkling like diamond dust. You pass by the steadfast North Star, admiring the elegant beauty of Sirius. The universe is no longer scary or hostile, but feels like a warm embrace, cradling you as you sleep. The darkness of space is a gentle darkness, an absolute silence with no noise, no pressure. In that silence, your heartbeat slows and your breathing becomes more even. You feel so light, like a speck of stardust, floating lazily in the Milky Way's river of light. The heroic spacecraft, like Venera or Messenger, are now also at rest on those distant planets. They completed their mission of bringing the light of knowledge to humanity, and now they have merged with the grey rock and yellow-orange clouds, becoming a part of cosmic history. You too, after a long day filled with so many worries, it is now time for you to complete your mission and allow your mind to rest completely. The story of Mercury and Venus comes to a close, but it opens within you a profound understanding of the value of life. You appreciate every breath of fresh oxygen, every drop of cool water, and every gentle breeze on Earth. These simple things are the treasures that our neighbors longed for but could never have. With that gratitude, your soul becomes more serene and lighter than ever before. The light from distant stars is caressing you to sleep. A million years, a billion years, or the past 15 chapters, they are all just a blink of an eye in the flow of eternal time. Just let yourself dissolve into a deep slumber where there are no boundaries between reality and dreams of galaxies. Tomorrow, when the sun rises, a new day will begin with new discoveries. But for now, there is only you, the darkness, and the peace of the universe. The planets will continue their orbits, the sun will continue to shine, and mysteries will still be waiting for us up ahead. But that is a story for tomorrow. Now, close your eyes completely. Feel the warmth spreading from the soles of your feet to the top of your head. Every muscle is relaxed. You are sinking deep, so deep, into a sound and dreamless sleep. I wish you a sleep as peaceful as the silence of vast space. I wish you beautiful dreams of stars and distant planets. Knowledge before sleep bids you farewell. Sleep well, my fellow star traveler,